Good morning everyone. Welcome to today's session. So far we have been discussing about radioactivity and concept of compound nucleus. In today's session we will see the phenomenon of nuclear fission, chain reaction, some fundamental terms in nuclear reactors. We will see each topics. So let's begin the session. So all started with the experiment of bombarding uranium nucleus with neutron conducted in 1934 by Fermi. It was observed that several beta particle emitted, but it was assumed that uranium first split into transuranic elements. Later in 1938 Hahn and Strassmann showed that uranium is splitting into two intermediate mass nuclei, barium and krypton. Owing to this observation, Meitner and Frisch suggested that on neutron bombardment, the uranium nucleus splits up into two lighter nuclei. This splitting of larger nuclei into smaller one resembled cell division and hence was called nuclear fission. So, we may define the nuclear fission as the process of breaking up of nucleus if heavy atom into two more or less equal fragments with release of large amount of energy. The product nucleus appearing are called fission fragment. Fissions mainly to achieve stability. Just recall the binding energy curve in which we discussed that nucleus with intermediate mass number have more binding energy and hence are more stable. The general expression of fission is given in which uranium nucleus is bombarded with neutron. It first forms a compound nucleus. The compound nucleus later slits into intermediate nuclei along with a number of neutrons and an amount of energy Q. Few examples of nuclear fission of uranium is given. Note that the fission fragments, number of neutron is different in both cases. We need to know the amount of energy released per fission. First method to find this is using data from binding energy curve. From binding energy it's observed that for intermediate and heavy nuclei binding energy per nucleon is approximately 8.5 to 8.8 and 7.6 MeV respectively. In nuclear fission heavier nuclei is converted to lighter nuclei. So the difference in binding energy is obtained as 8.5 minus 7.6, which is 0.9 MeV per nucleon. We need to calculate the net energy released during fission, which is nothing but number of nucleon in uranium times binding energy difference per nucleon. That is 235 times 0.9, which is approximately 212 MeV. Second method to find the energy released using Q-Weil equation. For given reaction, just find the difference of sum of mass on reactant side and product side mass. The difference is represented by delta M, which we call mass defect. This mass is converted into corresponding energy by Einstein's mass-energy equation. Since one atomic mass unit is equivalent to 1 MeV, energy equation now become delta M times 931.3 MeV. Just substitute the valued, we get energy released per fission approximately 207 MeV 0 volt for above nuclear fission. Note that this large amount of energy is released within 10 raised to minus 8 seconds. When we studied liquid drop model we discussed of its advantage that with the model we can explain nuclear fission. Boer and Wheeler successfully explained the phenomenon of nuclear fission on liquid drop model. A liquid drop has a spherical form due to internal molecular forces responsible for surface tension. According to their theory, an excited liquid drop may oscillate in a number of ways. On applying a large external force, the sphere may change into an ellipsoid. If the external force is sufficiently large, the ellipsoid may change into a dumbbell shape and may even break at the narrow end into two portions. The analogy may be extended to a nucleus which behaves like a liquid drop. When a nucleus absorbs a neutron, it forms a compound nucleus which is highly energetic. The extra energy possessed by it comes mostly from the binding energy of the neutron absorbed by it. The extra energy may set up a series of rapid oscillations in the spherical compound nucleus shown as figure given. As a result of these oscillations, the shape of the nucleus may change at times from spherical to ellipsoidal shown as B. If the extra energy is large, oscillations may be so violent that stage C and ultimately stage D may be approached. The nucleus is now dumbbell shaped, stage D. Each bell of the dumbbell has now a positive charge and one repels the other. This results in a fission, stage E. The fission fragment may not be of same size. Uranium isotope 235 get excited even by absorption of an individual neutron, while 238 isotope of neutron require highly energetic neutron with energy a few MeV are required. In this context, let's discuss about chain reaction. A chain reaction is a self-propagating process in which number of neutrons goes on multiplying rapidly almost in geometrical progression during fission till whole of fissile material is disintegrated. Consider fission of uranium caused by a single neutron. The fission produce 3 prompt neutrons. These 3 neutrons in turn may cause fission in 3 uranium nuclei producing 9 neutrons. These 9 neutrons in turn may cause fission in 9 uranium nuclei producing 27 neutrons and so on. The number of neutrons produced in n such generations is 3 raised to n. It's like number of neutron is increasing in a geometric fashion. We define a term called multiplication factor K, which is the ratio of number of neutron emitted in one generation to the number of neutron in preceding generation. Depending on whether the number of neutron is increasing, decreasing or kept constant generation after generation of fission, we have 3 types of reactions built up: dying down or steady reaction respectively, FO, which is greater than, less than or equal to 1. Before going into the concept of chain reaction and reactor, we need to know few basic terms. Fast neutron and slow neutron are neutron with energy in order mega electrovolt and few electrovolt respectively. The material can be fissile, which means they are capable of undergoing fission by interacting with slow neutron. An example for such material is 235 isotope of uranium. Fissionable material are those material that can sustain the chain reaction only if colliding neutron have energy in the order of few mega electrovolt. An example for such a material is 238 isotope of uranium. Lastly, material is called fertile if the material is capable of absorbing neutron to create breed fissile material. In this context, just know that the process F converting non-fissionable material into fissionable material is called breeding. As for now, let's try to calculate the total amount of energy when 1 kg of uranium-235 undergo fission. There is Avogadro no. By 235, that is 25 into 10 raised to 23 number of atoms in 1 kg of uranium material. We already know that a fission process take place at 10 raised to -8 second with release of approximately 200 megaelectronvolt of energy along with release of 2.5 neutron on an average. Then total energy release is nothing but no. Of atom, that is 25 into 10 raised to 23 times 200 megaelectrovolt, that is 5 times 10 raised to 26 megaelectrovolt, that is 2.26 into 10 raised to 27 kilowatt-hour energy. Suppose it takes n generation of fission for complete 1 kg of material. Then 2.5 raised to n equals is 25 into 10 raised to 23. Just rearranging terms, we get n as 60. That is total of 2.26 times 10 raised to 27 kilowatt-hour of energy is released within 0.6 microsecond along with release of 2.5 raised to 6 no. Of neutrons. Large amount of energy is released during nuclear fission. Due to this reason, nuclear energy is being used for the generation of electricity. The most striking aspect of nuclear fission is the magnitude of the energy involved. Ordinary chemical reactions, such as those that participate in the combustion of coal and oil, liberate only a few electron volts per individual reaction. Most of the energy that is released during fission goes into the Ke of the fission fragments. The emitted neutrons, beta and gamma rays and neutrinos carry off perhaps 20% of the total energy. There are certain conditions to be satisfied for the chain reaction to occur. Let's consider a system consisting of uranium and a moderator. We know on an average 2.5 neutrons are ejected per fission. But all of them are not available for further fission. The maintenance of the chain reaction depends upon a favorable balance of neutrons, that is, the loss of neutrons must be less than the surplus of neutrons. We know the fission of uranium nuclei, which produces more neutrons than the number of neutrons used for inducing fission. But there might be loss of neutron also. Loss can be due to non-fission processes, including the radiative capture of neutrons by the uranium and the parasitic capture by the different substances in the system and by impurities, or due to escape or leakage of neutrons through the surface of the system. Let us consider a fissile material of size r. We know that neutrons are produced throughout the volume and hence the production rate of neutron is proportional to volume, that is a cube. The neutrons may escape through the surface. Hence, the escape rate is proportional to surface, that is a square. If we take the ratio of escape rate to production rate, we can see the RIO is inversely proportional to the size of material, that is r. That is larger the size of the body, the smaller is the escape rate. So, if we increase the volume of the system, the loss of neutrons by escape from the system is reduced. For maintaining the chain reaction, there is a critical size of system to be maintained. So we may define critical size as the minimum size of the fissile material for which number of neutrons produced in the fission process just balance those lost by leakage and non-fission capture. The mass of the fissionable material at this size is called the critical mass. Chain reaction is not possible if size of material is less than critical size or mass of material less than critical mass. It's seen that chain reaction is not possible in natural uranium. Why is it so? Natural uranium consists 99.28% of 238 isotope of uranium and 0.72% of 235 isotope of uranium. If you remember, 238 isotope of uranium need fast neutron to undergo nuclear fusion, while 235 isotope of uranium needs only slow neutron. The neutrons released during nuclear fission will try to bombard the nuclei of uranium-238 mostly, and very few uranium-235. Out of all neutron available, only few can cause fission of uranium-238, which is the major part of natural uranium. Hence we say chain reaction is not possible in natural uranium. Then can we make chain reaction possible in natural uranium? Of course we can. By using moderators. Usually used moderators are graphite, heavy water, beryllium, beryllium oxide, hydrides of metals and organic liquids. The function of moderators is to slow down the fast neutron through inelastic scattering. These slowed neutrons may cause the fission of uranium-235 to go up. When we choose moderators, we need to make sure that the material does not absorb much neutron and capable of scattering the neutrons. The reactions occurring in a self-sustained chain reaction is shown here. As you may see, a slow neutron bombarded at uranium-235 nucleus. The nucleus breaks into two fragments, 3 fast neutron along with an amount of energy fission process. Moderator may slow down these fast neutrons. 1 neutron may escape. 1 neutron may be captured by uranium-238 to form uranium-239, which decays to neptunium-239, and then to plutonium-239. 1 neutron is still available for carrying on the chain reaction. It bombards U-235 and the process is repeated. This reaction is self-sustaining chain reaction. There are 2 types of chain reaction in one. The chain reaction is first accelerated so that the neutrons are built up to a certain level, and thereafter the number of fission-producing neutrons is kept constant. This is controlled chain reaction. Such a controlled chain reaction is used in nuclear reactors. In the other type of chain reaction, the number of neutrons is allowed to multiply indefinitely and the entire energy is released all at once. This type of reaction takes place in atom bombs. The release of this tremendous amount of energy in such a short time interval leads to a violent explosion. This results in powerful air blasts and high temperature of the order of 10 raised to 7 Kelvin or more, besides intense radioactivity. Hence is more hazardous. Atom bomb, which is one of the hazardous nuclear weapon, works on the principle of uncontrolled chain reaction. An atom bomb consists essentially of 2 pieces of uranium-235 or plutonium-239, each with size smaller than the critical size and a source of neutrons. The 2 subcritical masses of uranium in the form of hemispheres are kept apart by using a separator aperture. When the bomb has to be exploded, a third well-fitting cylinder of uranium, whose mass is also less than the critical mass, is propelled so that it will fit in or fuse together with the other 2 pieces. Now the total quantity of uranium become greater than the critical mass. This will initiate uncontrolled chain leading to a terrific explosion. We know that during nuclear fission enormous amount of energy is released. But all these happens in fractions of seconds. Nuclear reactor is the device in which chain reactor is controlled so that energy is released at a given rate. This energy can be then used to produce electricity, and such reactors are called power reactor. Another fission reactor is breeder reactor, which produce more fissile material than it consumes. Let's see the components of nuclear fission reactor. Let's discuss the different components of nuclear reactor. The fissionable material used in nuclear reactor is called fuel. Generally we use uranium-233,238 and plutonium-239 is used as fuel in form of cylindrical rod arranged in a regular pattern in active reactor core. This is kept in a chamber which is filled with material containing light nuclei called moderator. The purpose of moderator is to slow down the fast neutron by elastic collision, since slow neutron have more tendency to cause fission. The core is designed in such a way that out of 3 neutron emitted pre-fission, one of them is used to continue the fission reaction. That a steady chain reaction is maintained. Water, for an example, in Apsara reactor in Bark, Mumbai, heavy water and some other reactors in India, and solid graphite are some of the moderators used. Yet another component is by the use of reflectors on the surface of reactors, leakage of neutrons can be very much reduced and the neutron flux in the interior can be increased. Materials of high scattering cross-section and low absorption cross-section are good reflectors. Water or molten salt is circulated past the reactor core to absorb heat generated in the core. Hence they are called nuclear coolant. They takes away the heat from reactor and then used to generate steam. The function of control rod is to maintain controlled steady chain. The control rod must have properties like large neutron absorption cross-section. As rod pushed into the core, neutrons are absorbed, cutting down the reactivity. Similarly, to increase the rate of reaction in core, you need to pull up the rod so that less neutrons are absorbed and fission builds up. Usually cadmium or boron rods are used for this purpose. Yet another component is safety system that protects the space surrounding the reactor against intensive neutron flux and gamma radiation by building up concrete wall of 1 to 2.5 meter thickness that can absorb radiations and neutrons to an extent. Now that we know the function of various components, let's see working of power reactor, in which the energy from reactor is used to produce electricity. As you may see, the reactor has fission reactor as primary part. The heat generated in primary part is used to power in a nuclear power plant. A quantity of enriched uranium in the form of pure metal or solution of a soluble salt in water constitutes the center of the heat energy source. A large quantity of heat is produced in the fission process. The cadmium rods regulate the temperature to a predetermined value. If it is desired to bring down the temperature, the cadmium rods are pushed down further as to absorb more neutrons. If the temperature has to be raised, the cadmium rods are pulled up a little. A fluid is circulated through the shielded reactor and heat exchanger. The hot fluid, while flowing through the heat exchanger, converts water into steam. The steam produced runs conventional turbines to produce electricity. This method has got advantage that more power with less amount of fuel than conventional methods. But we are at disadvantage when we think about the difficulty in disposing the fission fragment, which are radioactive, and maintenance of large equipment. Let's see what is a breeder reactor and what is its difference from the reactor we discussed earlier. Well, in breeder reactors, fast neutrons are used to initiate nuclear fission, and as the reactor operates, it creates more fissile material than it consumes, making it an efficient way to generate nuclear fuel. This process of converting non-fissile material into fissile material is called breeding reaction. In earlier case, we discussed the need of moderators. But in breeder reactor we don't need such a component, because in this reactor both slow and fast neutrons are produced. And in breeder reactor operating temperature is very high that we use liquid sodium as coolant instead of water or heavy water. Now we will discuss about 2 types of breeding reaction, one initiated by fast neutron and another by a slow neutron. This is breeding reaction initiated by a fast neutron. 238 uranium isotope captures fast neutron to go to excited state of uranium-239 isotope. It comes to ground state by emitting a gamma particle. Later uranium-239 undergo beta-negative decay with half-life 23.5 minutes to form neptunium-239 and again undergo beta-negative emission of plutonium-239 with half-life 2.35 days. When plutonium undergo fission by 1 MeV, the average yield of Newton per absorbed neutron is of 2.7. One or more neutron emitted by fission of 239 plutonium is captured by 238 isotope of uranium, breeding more fuel than it consumes. This is one of the advantage. Another advantage is that these type of reactor does not need moderator. Not only this, breeding reaction in thorium is possible by mere capture of slow neutron. Let's take a look into that. This is breeding reaction initiated by a thermal neutron. 232 thorium isotope captures thermal neutron to go to excited state of thorium-233 isotope. It comes to ground state by emitting a gamma particle. Later, Thorium-233 undergo beta-negative decay, palladium-233 and again undergo beta-negative decay to form uranium-233. Here also more fissile material is created than consumed. Fission reactors got many advantages and disadvantages. The energy from fission reactor can be used to generate power. We can use them to large number of radioisotopes. For this, a suitable compound is drawn into the center of the reactor core where the flux of neutrons may well be more than 10 raised to 16 per meter square per second. An example is manufacturing of sodium-24. Also we may use nuclear reactor to produce a number of radioactive materials needed for research purposes. These isotopes are sometimes used in medicine, agriculture since reactors provide a huge source of neutron. Useful radioisotopes have been artificially produced and several nuclear reactions have been studied. We may also study the effect of neutrons on biological tissues, study radiation damage etc. However, the maintenance of fission reactors are difficult, and there is risk of radiation and contamination due to nuclear waste. So in this session we say the concept of nuclear fission, working of nuclear reactor, reactions involved in them and why we choose them for energy production. But as the source of energy we choose fission over fusion. In next session we'll see what nuclear fission and why do we chose them over fission. So, see you in next class. Thank you.